Yeah. Okay. Good morning, everybody. It's a pleasure to have Gavril Farkas from Humboldt University, who is in Hungary right now. And he speaks on resonance and Chen invariants in geometry.
Yes, so yeah, thank you very much for this invitation. And yes, I mean, I could say I wish I was in Atlasov. I wish I wasn't. I was in Atlasov until very recently, actually. But now I'm in Hungary, and I will talk about. So I reformulated the title as resonance and Chen invariants in geometry in a little more broad setting. And my goal today is just to present some this circle of ideas, which has applications to a lot of groups of geometric nature. Some appear in hyperplane arrangements, some appear in mapping class group and Torelli group theory, and some there are also purely algebraic geometry applications, which are quite important, but maybe I won't say much about those today. So right, so let me begin. And so saying the following, so yeah, it's a motivating example, is that example of the hyperplane arrangement. And so I'm not going to go much into this, just as a level of some general ideas. So suppose you have a hyperplane arrangement. So some hyperplanes and hyperplanes in some complex, let's say it's a complex hyperplane arrangement. So this is a hyperplane arrangement in C to the L. So surely we all know some examples of this. So then the standard thing to consider is the complement. Yeah. And to this, this is a very interesting topological object. And there is a fundamental question whether geometric objects associated to XA are in effect combinatorial or not. And so which invariants of XA are combinatorial? And what does that mean, combinatorial? Well, usually people mean by this that they are determined by what's called the intersection lattice, i.e. determined by the intersection lattice of the arrangement. And this is L sub A or LA parenthesis A. So this is, you retain all the intersections of the hyperplanes, where A prime is a subset of A. So this is what is the combinatoric, so to say. And well, there is, of course, this is a theory which has been going on for 50 years or so. And there is a number of important results. So for instance, one important result is due to Orlik and Solomon, which says that the homology is combinatorial. And is combinatorial or matroidal. And not only that, they actually proposed an algorithm. They put forward an algorithm of computing, describing entirely the homology. Then there is, of course, another very important invariant is the fundamental group of the arrangement. So GA is the fundamental group. And it turns out that this is not combinatorial. And I will not go into details in this much. And it's also, I have to say, it's not entirely my area of expertise. I will move a little away from it in a second. It's not combinatorial, but quite interestingly, the lower central series ranks of it are. But the ranks of its lower central series are combinatorial. Nevertheless, so you have a group, and you consider, I will describe in a second the lower central series, and you look at the quotients. and those are abelian groups, and the ranks of these are the lower central ranks of the hyperplane arrangement. And well, there is also the question of how to, not, they are determined by the intersection lattice, but then the next question would be, are they in fact determined? Is there a formula, a concrete combinatorial formula that expresses these ranks? And this is not known. In fact, seems to be a major open problem. And in fact, there are negative results saying that there cannot be a universal formula that works in all the cases. There are other invariants, and these invariants are in some sense the main actors of this talk, and these are the Chen ranks. And the Chen ranks of the arrangement are in fact combinatorial. And there has been a conjecture of Suchu, which I will recall, well, I will present, putting forward a formula for these Chen ranks. And the talk is about the resolution of this conjecture. But at this moment, I should discuss, because surely not everybody knows, what are the Chen ranks of a group. And of course, please interrupt me whenever there are questions. So what are the Chen ranks of a group? So suppose I start now with a G, a finitely generated group. And you should have in mind, you know, say a fundamental group of hyperplane arrangement, a fundamental group of compact Hilbert open a smoother projective algebraic manifold, or Torelli groups, and so on. So you form then the lower central series of the group, just like you learn in algebra 2. So you start with gamma 1 of G, this is G, and then you start taking commutators. And right, so you have something like this. And here, gamma q plus 1 is the commutator of gamma q and the group itself. And therefore, the quotients are abelian groups, and they are finitely generated abelian groups, and they have ranks. And then you call phi q of G to be, per definition, the rank of this abelian, or finitely generated abelian group, gamma q of G divided by gamma q plus 1 of G. So these are the lower central ranks of G. So computing them is in general quite difficult. And this is a very non-commutative problem, if I may say so. And so algebraic geometry cannot really contribute much to this. And now you can do something which at first you can abelianize slightly this problem. And this means of passing from G to the Metabillion quotient of the group. So first of all, you consider G prime, which is gamma 2, which is the derived group. And then you can derive again. So this is G prime, G prime. And then you replace G by G divided by G over double prime. So this is called the Metabillion quotient of the group. And then here is the definition. The Chen rank is denoted by theta. Theta of G is per definition the lower central rank of the derived group, of the Metabillion group. So this is the definition. Okay. So this is an invariant, which is subtle invariant, and it's quite remarkable. So the reason for considering it is, above all, is that you can attack this the study of its invariants with methods of commutative algebra, of exterior algebra, and actually of algebraic geometry. So these are in some sense much better behaving invariants. And also they are very subtle invariants that there are cases, often cases of hyperplane arrangements which cannot be distinguished by their lower central ranks, but they can be distinguished by their corresponding Chen ranks. Okay, so yes, so then I will go to the second page. Right, and so these invariants, of course, have been introduced by Chen. Yeah, so maybe I start here copying what it is again. So this is theta q of G. So this is the rank of gamma q of G over G double prime divided by gamma q plus 1 of G over G double prime. So why are they so much better behave? Well, because of the connection with Alexander invariants. And so here, this is a piece of mathematics with a prodigious history, and it goes actually to starts with knot theory. And these Alexander invariants, so they were sort of course, connected to the Alexander invariant of knot, and they were various presentations of the complement of the knot. Yeah, but the theory itself can be set up for any group. And in fact, we are going to go even a step higher, further than that, by actually leaving topology behind altogether. So what is this? So this Metabillion group is called Metabillion because it sits in an obvious exact sequence. So here I have G prime over G double prime. And here I have the abelionization, G over G double prime, G prime. Yeah? So you have something like this. And so this is the abelionization of G. And this is the abelionization of the derived. And metabillion means an extension of a billion by a billion. Yeah? That's metabillion. Okay, and the point is now you set now, so here is the definition of this Alexander invariant, is you set BG, definition, BG is simply the homology of the derived group. So it's the abelionization of the derived group. You can take it with Z coefficients, or if you are not interested in torsion, then it's rational or complex coefficients. So this is G prime divided by G double prime. And now the point is, if you look at this sequence and you think about it for a couple of minutes, you see that this, in fact, can be viewed as a module over the commutative ring over the abelionization of G over Z of G abelionized. And this is, of course, a commutative ring. And now we are in commutative algebra. And the action is by conjugation, by the way, right? So it acts by the multiplication by square is by conjugation. And then furthermore, so where does this chain ranks appear? So you introduce the augmentation ideal inside inside this ring. So this is the augmentation ideal. So the sum of all elements whose coefficients are this integer coefficient sum up to 0. So this is the augmentation ideal. And then it is a fact which is really essentially elementary in the sense that if one looks at it, I mean, you can just, yeah, that you have the following canonical isomorphism. So this augmentation ideal multiplied by powers of this augmentation ideal gives a grading. You can consider graded objects associated to the Alexander invariant. And there is a canonical isomorphism between the following two objects, IQ times BG divided by IQ plus 1 BG. And the graded piece of the Metabillion quotient. But you have to do a shift by 2. So this is the point here. And this is, as I say, is essentially elementary. In the sense you look at the left-hand side, you look at the right-hand side, and if you think a little bit, you will get a map, and then you prove that this map is an isomorphism. And this is so usually, as I say, it's rather easy, and it has been, I think, observed first by Massey. Okay, but now, so I can summarize this now, this discussion that basically this chain ranks, so this the Q plus second chain rank of G, then is accordingly the rank of this abelian group. So it's the rank of the Q'd graded piece, and this is the grading piece with respect to the augmentation ideal of the Alexander invariant, right? So this is what I wanted to summarize here. And this is now an object that belongs firmly to commutative algebra. And there is, of course, a question of how to compute it. Okay, right. So this is it's absolutely general stuff so far. And so how to compute this? And in general, so there has been here, there is a lot of work here which goes back to Chen. Of course, he wrote a bunch of papers on this. That's why they are called Chen ranks, and he developed this Fox calculus for computing and so on. Then there was Dictain and Sullivan, and then goes a lot of work of part of these people are my co-authors, and these are Papadima and Suchu. Papadima unfortunately passed away. So, etc. And there is a way of computing the so-called infinitesimal Alexander invariant, and this leads to what's called Causal Models. This is the word. I mean, this is a long strip in some sense, and it didn't exactly go straight, but there is a machinery, and this goes under the name of Causal Modules for computing the understanding the graded object associated to the Alexander invariant of a group. Okay. So, any questions about this group theory part? If not, then I go with the definition of Causal module. So now this is a purely algebraic definition. I started with hyperplane arrangements, then I put myself in a more general setting by discussing arbitrary groups, and now I leave the groups altogether, and I start with something algebraic. And of course, I will go back to all this. So what are these Causal modules? So it's a tool for computing these invariants, but they can be done in the following. It can be set up algebraically. Namely, you start with a K vector space. It doesn't even have to be in characteristic 0 but finite dimensional. And well, maybe I don't want this K here. It's just a vector space, yeah, because I have okay. And then I have once and for all, I fix a subspace K, capital K, in wedge 2V. This is fixed, a linear subspace, fixed. And what I have to say is subject to this choice. Now, I form the Causal module, the Causal complex, and I'm hoping that you have seen this in some way. So you first look at the symmetric algebra, yeah, which has a grading over V, and then you look at when you compute Tor factors in homological algebra, you introduce Causal cohomology, the Causal complex. And basically what it does, it resolves the ground field, say C if you want, by free modules, by graded phi modules over the polynomial algebra. That is what the point of the Causal complex. So let me write it down. So I have a piece of it. So I look at the wedge 2V tensor by S. Here is V tensor by S shifted by 1. And here is S shifted by 2. So there are the differentials here. This is differential delta 1, delta 2. And then I have here wedge free V tensor S shifted by -1. So this is delta 3. Now the point here is that I have shifted, usually the Causal complex is wedge free V S shifted by -3. So I have here a shift by 2 in the Causal complex for some reason, but that's all. Yes. And then I take, yes, so what are these, right, so I take, I can take the quotient now. K is this fixed linear subspace, so I can divide, and I can take the quotient of wedge 2V by K, and I can consider the composition. So this is pi. So this is a morphism of graded S modules. And here comes a definition, which at first sight, if you haven't seen it, looks maybe peculiar. It says that, so I call the Causal module, which for some reason is denoted by W of V and K. So V, a vector space, K, a subspace, wedge 2V, is simply the co-kernel of pi as a graded S module. I will spell it out in a second. It's an absolutely central definition to the talk. So what is this? I will describe the kth piece. The kth, so for each Q, the qth piece of this is a finite dimensional vector space, and they form together a graded S module. And WQ of V and K is by definition wedge 2V Yeah, so when I write this degrading, yeah, so you see that the Q grading here, wedge to V tensor S is wedge to V tensor SQ, where SQ is the degree K polynomials. And then I have here SQV, and I mod this out by K tensor SQV plus the kernel of delta 2Q, where delta 2Q is the Causal differential. Yes, so I take right, but the Causal differential is exact. So by applying the isomorphism theorem for modules, this is the same thing as the cohomology of the following complex. I have here K tensor SQV, and then goes to V tensor SQ plus 1V, and then goes to SQ plus 2V. So the symmetric powers, and here is the Causal differential delta 2Q, and here is delta 1Q plus 1. So maybe I should say what is the Causal differential. So the Causal differential here sends an element of type V1 wedge V2 tensor say U. So V1 and V2 are in K, are in V, sorry, U is in SQ of V, and it sends it to V1 tensor V2U minus V2 tensor V1U. And delta 1Q plus 1 is just a multiplication. And of course, they form a complex and take the cohomology of it, and that's exactly this. And this is basically just the content of the fact that the Causal differential is in fact exact. Okay, so this is the thing. And the Causal module of a pair. So this is a totally algebraic construction, and it's actually surprisingly useful in a variety of contexts, as I will describe. Okay, so what is this? As I say, this is totally algebraic, can be done over any field, and you can start to play it by taking, seeing what happens if K is 0, for instance, yeah, and so on. But what is the connection to group theory? I should go back to this, and this is summarizing work of, say, Sullivan and Papadimasuchu. I should say, okay, first of all, if you have G is a group, if G is a group, you can consider a Causal module in the following way. You take simply V, the vector space, to be the homology. It's a finite, it's just the Abelianization with complex coefficients. Then the V dual is, of course, the co-homology. And then I have to give you a K. So I will give you first the K perp, the orthogonal. K perp is just the kernel of the cap product map, of the first cap product map. And this is from wedge 2, age 1 of G, the level of cohomology, into age upper 2 of G. And then I set VG, WG, so this is the Causal module of the group, as being simply the Causal module associated to these choices, namely to the choice of the cohomology and K, where K is the perp of the perp, of course. So this is some sort of homological gadget that you can associate to any finitely generated group out of the first cap product map. And by the way it is constructed, the first cap product map makes no difference between G and G over G double prime. So passing to this Metabillion quotient is insensitive. I mean, it cannot be seen in the first cap product map. So whatever invariant you can construct in this way is going to be an invariant, not of the group per se, but of its Metabillion quotient. And here is the setting here. So here is the summary of what is being written here. So it's a fact of work of all these people, and there are others. So my history is not complete here, but never mind. Is that I have that first of all the Chen invariant theta q plus 2 of G is, as I described, this is by this observation of Massey, is the dimension of the grade of the acute piece of the Alexander invariant. Maybe you complexify it. And now comes the new thing, and this is less than or equal to the dimension of this causal, of the Qt piece of the causal module. This is the fact. Maybe I give it even a different color. So this is a crucial fact. And in fact, you have that effect with equality if G is one formal. And this is one formality in the sense of Sullivan. So one formal, I don't want to make a formal definition of one formal. It basically says that the rational homotopy type is so a space is one formal if its fundamental group is one formal, and that means that its rational homotopy type is encoded in the homology, in its homology algebra. And if you want really full definition, it almost is the same thing as saying that here you have equality. There are lots of important results of people like Sullivan, Morgan, and so on, which says that important classes of groups are one formal. For instance, fundamental groups of smooth Kähler manifolds are one formal. Hyperplane arrangement groups are one formal. So fundamental groups of complement of hyperplane arrangements are one formal. The Torelli group is one formal. The Torelli group for the free group is one. No, maybe that's not one formal. The last one, but the Torelli group for the mapping class group is one formal. So there is a large class of one formal groups. Okay, so this is the summary of the where we are getting into this picture. So I started with this lower central series invariants. I introduced as an intermediate object this Alexander invariant, and then the Causal module, and there is a connection between the two. And in fact, you can compute Chen invariants of groups by looking at these Causal invariants. Okay, and so that's the story so far. And I should say, so I have introduced, right? So we have introduced this, so to this K in wedge 2B, we have introduced this Causal module. So this is a module over the symmetric algebra. I should say something here, that these invariants are, there are literally hundreds of papers, like many hundreds of papers on invariants that look like these, but they are considered as module over the exterior algebra. And this is the word of these quadratic algebras. And what we do here is that there is this BGG Bernstein-Gelfand correspondence between modules over the symmetric algebra and complexes over the, modules over the symmetric algebra and complexes over the exterior algebra. And we apply this BGG correspondence without saying so. And our definition of Causal module that we have here is already takes this BGG into account. So for me, it's much more reasonable to work with modules over the symmetric algebra and than with module over the exterior algebra. But these objects have another incarnation as well. Okay, so this module, there is a fundamental concept question now. When is this module, say, of finite length? When only finitely many pieces of it are zero. And this, what is the support of this module? That is something that you can ask, and people asked before. And you get to the last concept I want to introduce here, and maybe to the concept of resonance. And the resonance is something simpler than the Causal module. So K is a subspace in wedge 2B, and I define the resonance of this pair as simply the space of the set of those elements in V dual with the property that there exists a B in V dual, not proportional to A. So A wedge B is not zero. And I ask that this lie in K perp. So this is a tensor of rank 2 in K perp. So this is lying in K perp means that as a linear form should vanish when STTP K. Okay, and I add to it 0. Yeah. So this is a subspace of V dual. This is the resonance. And it turns out, as I said, so what does it mean that the resonance is 0? So the resonance is 0. This is already an interesting question. The resonance is 0 when there is no such B. Yeah. So what that means that no matter how I wedge two forms, I don't land in K orthogonal, in K perp. And this is something that can be written in terms of projective algebraic geometry very, very nicely. Namely, it says that if I take the projectivization of K perp and I intersect it with the Grassmannian of two planes in V dual, I get is empty. And this is intersection being taken inside the Plücker embedding of the Grassmannian. Okay, because that's exactly what you have to know here is that the Grassmannian can be realized as the space of pure tensors in wedge 2D. Is a basic fact of linear algebra in some sense. I wouldn't call it even algebraic geometry. It's more basic than that. So, okay, and in particular, the resonance, if the resonance is 0, then necessarily the dimension of K, and say the dimension n is of dimension of V, then the dimension of K has to be at least 2 times n minus 3. This is another thing I want to say. Yeah, so this, I hope this is basically because of the fact that this is the Grassmannian G2n. So this has dimension 2n minus 4. And then the 2n minus 3 comes from here. And you understand this, that if K is, for instance, too small, then K orthogonal is too big. And the projectivization of the K orthogonal will intersect the Grassmannian purely on 4-dimensional reasons. So this is not an equivalence, it's just an implication. But it tells you that the resonance can be trivial if and only if K is very large dimensional. Okay, and I should say something that this was observed by Papadimasuchu in an important paper, that in fact the support of the causal module, they didn't quite formulate it like this, but this is what essentially is the case, is in fact the resonance. So the causal module is a finite length, only finitely many pieces will be non-zero, if and only if the resonance is trivial. And this is actually the first thing that we study. So can we make this more precise? And here is a theorem that we proved in, well, it's now really 4 years ago with Mariana Produ. Then, so myself, Stefan Papadima, in some sense, initiated the entire project, Claudio Raico and Jerzy Weimann. So this is 2018, has been published. So we said, what? Okay, the question was, assume the resonance is 0. What can we say? We know that there is some vanishing of the causal module from some higher range. What can we say? When does this vanishing really appear? And what can we say about the pieces of the causal module that do not vanish? And here is the theorem. Our theorem is optimal in this sense. So K is fixed in wedge 2D. And it says the following: assume the resonance case is chosen so that the resonance is 0, is trivial, which means exactly this condition that I described here. This condition, which from the point of view of algebra geometry is very, very, very simple. Just means that this linear space is disjoint from the Grassmannian. Then this is equivalent. Yeah, so the dimension of V is n. Okay, this is equivalent to the following vanishing. Wn minus 3 of Vk is 0. And actually, this is the theorem. And I should say here that this is in fact equivalent, and this is immediate, that this is equivalent to saying that all the higher pieces vanish as well. I should say that from the definition of these causal modules, if WQ is 0, then WQ plus 1 is 0 automatically. So we just have to find the first one which vanishes. Okay, and furthermore, we also determine the Hilbert series of this causal module, and we prove that the dimension of WQVK is at most n plus q minus 1 choose q times n minus 2 times n minus q minus 3 divided by q plus 2. And this is for all in the range where the resonance doesn't vanish. So this is the theorem. This is the theorem on vanishing resonance. Yeah, so when the question is, all right, so if the resonance vanishes, so this is an algebraic condition, can be applied for any causal module. Should it come from topology, from algebraic geometry, doesn't matter. If and there are plenty of examples, if the resonance is 0, then you have this vanishing of the causal modules. And in fact, you have this inequality, and you have equality in the case of equality with equality in the extremal case, extremal with respect to the property that the resonance be trivial. And this is when the dimension of K is of dimension K is 2n minus 3. Okay. So this is not so new, but I mean, to what I have to say, I have to mention this, and there are lots of applications of this theorem, so I mentioned only one here, maybe because because of the maybe audience in mind. So this is the application. I mentioned the application to Torelli groups. So application to Torelli groups. Yes, so right. So you know what the Torelli group is. So you start with a Riemann surface. Yeah. So here's a Riemann surface, sigma G. And you consider the mapping class group. So this is the mapping class group. Yeah. So these are the outer automorphisms that on phi, the positive respective orientation of the fundamental group of the Riemann surface. And then, of course, each such automorphism induces an automorphism on the homology. So I take the homology, and let me ignore the torsion phenomena. This is the homology of the Riemann surface. So this is just Z2G, but it comes with an alternative. It comes in out with an alternative form. And there is a surjective morphism over the symplectic group. So these are the automorphisms of the homology, right? And this is surjective. And you know that, so this is here. This here is the orbifold fundamental group of MG. MG is the moduli space of curves. And this is the orbifold fundamental group of the moduli space of abelian varieties. And the kernel is called the Torelli group, you know, because of the Torelli map, which relates these two prominent moduli spaces. And this is a very subtle group, and it measures at the level of homotopy the difference between the moduli space of curves and the moduli space of abelian varieties. And yes, so I should say this has been studied above all in important papers of Dennis Johnson, and it has been observed that unlike the mapping class group, which is its own derivation, which has no interesting abelianization, the mapping class, the Torelli group, has an interesting abelianization. And Johnson proved that, in fact, if you look at H by constructing what's called the Johnson homomorphism, that H1 of TG is canonically isomorphic to wedge-free HQ divided by HQ. And here you embed the first homology in wedge-free by capping with the fundamental form of the surface. Yeah. So in particular, the Betti number of this group is 2G choose free. The Torelli group is 2G choose free minus 2G. So this is a large abelianization. And as I say, there is a lot. The study of this group is a major problem in geometric group theory, Teichmuller theory, and there is a lot of results here. So first of all, this group is one formal. This is a theorem of decaying, and the resonance of TG is trivial. This is another theorem of Dimka and Hein. I believe Dimka, Hein, yes, maybe. I'm not sure there is not a third order in this paper, I don't know. Then there is finally a very interesting result that which you look at the Alexander invariant of the Torelli group, that this is nilpotent. Tg divided by Tg double prime is nilpotent. It's only a few years ago, 2019, and this is due to Herschel and He. So we are in a very good shape to apply our previous theorem here, which says that if the resonance is zero, if the resonance is zero, then we have this vanishing depending on the dimension of the space, and the dimension of the space in this case is the first Betti number of the spacing of the Torelli group. So we apply this, and what we get is that this theorem applies in this case is that the nilpotency class of the Metabillion quotient of the Torelli group is at most the Betti number minus 3. 2g choose 3 minus 2g minus 3. And the virtual cohomological dimension as well, but here the virtual cohomological dimension is also the same thing, but here minus 2. This is just the previous theorem applied. Previous theorem applies. So this is kind of, in some sense, miraculous that we get a non-trivial result by applying a purely algebraic consideration without doing any serious analysis on the Johnson kernel and the geometric topology. Right? That is somehow remarkable, I find. And it says basically that these facts are encoded in this algebraic structure associated to Causal Models that you can associate to any group, to any space if you want. Okay, so there are similar results for, this was the Torelli group of the mapping class group. There is a similar result for the Torelli group of the free group, and maybe I'll be brief about this Torelli group of the free group. So this has also trivial resonance. Yes, and this leads to the outer space and to the what is nowadays called the moduli space of tropical curves. So you have the outer automorphisms of the free groups on G generators. And then you look at the surjective map to the general linear group. And this is the Torelli group. And so when you take the outer space and you mod out by this group, then you get just like the particular space. Now you will get not mg, but mg trop. Yeah. And then you get a similar result that OAG divided by OAG double prime has a virtual nilpotency class. So virtual nilpotency class means the nilpotency class of any finite order torsion-free subgroup. Virtual nilpotency class of order less than the Betti number of this, which the Betti number of this has been computed by Cavazumi and Andreadakis. I don't remember exactly, but it's certainly known, this quantity. Okay, etc. So these are mentioned in this paper that, so in 2018-19, we put out two papers with Aprodu, Papadima, and the others. And one is entirely devoted to topological applications. Okay, so right. So now the question is going back to this theorem. Yeah. So this is all very nice, but what happens if the resonance is non-trivial? After all, this is a very serious restriction. There are interesting examples, but there are for many spaces the resonance will not be trivial. And can you have, in that case, you know that you cannot expect such a result. Each piece of the causal, each component of the corresponding causal module will be non-trivial. But can you compute their dimensions? Do you have a lower bound, sharp lower bound? And this is the topic of the work done this year. So now I have, okay. So page 6. Right. So what if the resonance is not trivial? The resonance does not vanish. And the example in mind here is that of hyperplane arrangements, because there the resonance is basically negative. And well, we will have a similar result, but assuming something about the resonance. You cannot have a result computing these causal invariants in terms of the resonance if you don't assume some good behavior properties on the resonance. And here comes the definition. So here's the definition. So remember, I'm in the setting when k is in wedge 2v, and I have this resonance, yeah, defined. And the resonance, I should say, it's in V dual. I can also projectivize it, and it's not only set, but it's in fact an algebraic variety. Because if I projectivize the resonance, this is I already described a couple of pages before. This is it corresponds to the intersection of k orthogonal with the Grassmannian or G or V dual. Yeah, so both are here. This is an intersection in a projective space, and this is endowed with a scheme structure with multiplicities. And I can talk about. I should take into account the scheme structure of this resonance. Not it's just a set theoretic definition. Okay, so now here comes a bunch of definitions. The resonance is said to be linear. So I have three definitions here. Linear if it's a union of linear subspaces. So I call them V1 bar. So these are subspaces of V dual. VL, yes, where VI bar dual should correspond to a subspace of V. Sorry, there is nothing. There is no bar. Okay, so right, and therefore this is essentially a quotient. So I have a quotient. So it's kind of confusing. It's very elementary, but confusing. So the resonance is a union of subspaces of the dual, linear subspaces. So this is a linear subspace. And there are finitely many of them. This is the first definition. The second condition is the resonance is isotropic. If each of these is, first of all, if it is linear, plus an extra condition, namely for any component, for each component of the resonance, VI bar dual, we have in fact a stronger condition, namely we have that wedge 2 of VI dual is in fact containing k orthogonal. So let me describe this. So this actually is something that comes from Hodge theory. It's algebraized, but it's behind this Hodge theory. So what are we requiring here? We are requiring the following thing. We are requiring, so if I have two elements, A1 and A2, so this is I, in VI dual, so they are in the resonance. That means that I can find the B1 and I can find the B2 in V dual such that A1 wedge B1 is in K perp, so restricted to K is 0. And H2 wedge 2 restricted to K is also 0. Yeah, this is per definition. But actually out of this, I would like to get that in fact A1 and wedge A2 is 0, because that's exactly what I'm asking. This is question mark. So when this happens, then the resonance is said to be isotropic. Of course, it's a good definition because there are large classes of examples when this is satisfied. And there is the last one is strongly isotropic. So strongly isotropic means that well, when I take now, I intersect K orthogonal and I look it with, I kept it with the ideal in the exterior algebra generated by this subspace VI. So this is the exterior algebra. I get precisely K, or I get precisely wedge 2 of VI. Now this is the one probably that is the most opaque. So, okay. So what have I said? I said this is strongly isotropic because this inclusion is isotropic. Yeah. I wanted that wedge 2 VI is in K per. It's of course in the ideal. So this is the ideal generator. And well, when I have in fact equality, I have strongly isotropic. So these are conditions, they have not been formulated in this way. They in topology papers, you see traces of this, but or in hyperplane arrangement papers, but this is a purely algebraic definition. It can be given for any subspace K in wedge 2V. So you can require 3 conditions under resonance. And I should say something here. So for instance, example, if X is a smooth projective variety, or it can be K as well, smooth projective variety. And G is the fundamental group of X. Yes. So first of all, the resonance here, I should say something like this. So the resonance is linear. With components corresponding to vibrations over Riemann surfaces of components corresponding to vibrations over Riemann surface of genus at least 2. This is a Riemann surface of genus, so hyperbolic Riemann surfaces. So the point here is this what something called the Castello-de-Frankis inequality. So when you have two 1 forms on a variety, they wedge to 0 if and only if they are pulled back from a Riemann surface of from a hyperbolic Riemann surface of genus at least 2. This is the Castello-de-Frankis theorem. And then you can index the components of the resonance in terms of the various vibrations your variety has over curves or algebraic curves. If there are no such vibrations, the resonance is trivial, and the previous theorem applies. And now the isotropic condition in this setting is not satisfied. It's something called one isotropy. So isotropy here, I ask that this condition at H1 wedge 2 is actually 0, is K per. Well, one isotropy means that all such elements are not that they are 0, but in fact they are proportional. And this is because H2 of a Riemann surface is one-dimensional. It's not trivial. But anyway, it's almost satisfied. Isotropy, strong isotropy is more mysterious in general. So I should say something that there is further results here. Then if X is, say, quasi-projective, so you have a projective variety and take out some hyperplanes or some divisors out of it. So if X is quasi-projective, the resonance is linear, certainly linear, but it's isotropic if and only if the corresponding mixed Hodge structure on the H upper 1 is pure. So Rx is isotropic if and only if the mixed Hodge structure on H1 of X is pure. So this is not these definitions make some sense. That's all I want to say. There are strong isotropic is more mysterious and it has not been studied systematically, but it does appear in hyperplane arrangements. And in fact, so this is results of Suchu and Chen and Cohen, that if X is a hyperplane arrangement and so forth, if X is a hyperplane arrangement, XA maybe, then the resonance of this, so this is the resonance of the fundamental group, is in fact strongly isotropic. But our theorem that I will put in a second is not only for hyperplane arrangements. It's really for all the possible examples of causal modules that appear in mathematics for which these conditions are satisfied. Okay, but there is a large class of examples when these hypotheses are fulfilled. Okay, and then here is the theorem. And this is with Mariana Produ Claudio Raicu and Alex Suchu, from this year, that again, K is in wedge TV, so I'm looking at the most general Causal module. If RVK, if the resonance is strongly isotropic, and the resonance is a union of, first of all, it has to be linear, right? It's container definition. And I have these components, linear components. Then the following, then for any, and so the dimension of, for any Q bigger than the dimension of V minus V, so it's the same bound as in the vanishing resonance condition, you have the following, that the dimension of VQ of VK, so this is the causal, the component of the causal model associated with it, will be never zero this time. It's the sum from 1 to L of the dimension of WQ, and here comes the various components of the resonance, VI and 0. And of course, this can be computed. If I put here, this is a linear space of some dimension, and this the space in question is trivial. So this is then written as K plus 1 times the sum over all n greater than 2 of H_m times m plus q choose q plus 2, where H_m is the number of components of the resonance having dimension. Dimension. Okay, so this is the theorem. And let me, my time is almost up. So what is that saying for hyperplane arrangement groups? For hyperplane arrangement groups, it says that, so these quantities here, by the way, are the Chen invariants associated to the free group. And yes. Right, so I should say here remark. If I look at the theta q plus 2, so the Chen invariant associated to the hyperplane arrangement to the free group in n generators. So I told you that this can be computed from the causal module by right. In this case, in the free group case, the kernel of this k is actually trivial, right? So because the K product is trivial, so this is in fact k plus 1. Q plus 1 times m plus q choose q plus m plus q choose q plus, I should have said this, right? This is part of Chen, of course, obtained this with Fox calculus 50 years ago or 60 years ago in a different way, but it follows from this theory. And then how does the theorem look like? So for a hyperplane arrangement group, so for any hyperplane arrangement, you have the following thing. So G is the fundamental group of the arrangement. For any Q, which is at least the Betti number of the group minus 3, you have that the Q plus second Chen rank of this group is in fact the sum when m is greater than m of H_m, and here comes theta q plus 2 of the free group, where the formula for the theta for the Chen invariant of the free group is here, and H_m is the number of components of resonance which are of dimension n. Now, I won't have time to discuss how the resonance is presented for a hyperplane arrangement group, but this is combinatorial, and this is due to Falk, Zvinsky, and many others. This is a combinatorial recipe for constructing. I give you a hyperplane arrangements. Then there is this. You have a presentation in matroidal terms, in terms of multinets of this invariant. This actually tells you that not only that these Chen invariants are combinatorial, but it gives you a combinatorial formula for their expression. So, right. That's maybe all I wanted to say. The theorem here, in principle, there is a version of the theorem for scalar groups, as I say, of this theorem, because this the hypothesis of isotropy is not fulfilled. It has to be replaced by one isotropy, but it's just a minor distinction. And then there is a chain rank formula for the fundamental group of any, say, smooth projective rank as well. So I think I will stop here. Thank you for your attention.
Thank you for your talk. Questions and remarks, please.
I had a small comment or question.
Go ahead.
Oh, can I? Yeah, thanks. So you began discussing these the Chen ranks, and you were saying that some of them can't be interpreted combinatorially, and your definition was that it can't be obtained from the Euler-Solomon algebra, I think. So I was wondering the following: that there's a theorem due to Bailenson, which was never published and is not very well known, but it's very powerful, and it says that the associated graded pieces in the unipotent completion of the fundamental group of a topological space, a nice topological space, are given by its cohomology, and more precisely the cohomology of the products of the space with itself relative to diagonals. So you start with X, and you take, for example, the cohomology of X cross X relative to the diagonal, and that is shown by Bailenson to be isomorphic to the associated graded piece in the affine ring of the unipotent completion. And so if you do that with a hyperplane arrangement, you're going to take products of the complements of hyperplane arrangements relative to diagonals. And so that's basically just a big hyperplane arrangement with two types of hyperplanes, ones which you remove and ones which you take relative to. And there's a complex which calculates this relative cohomology built out of the Euler-Solomon complex. So I think Clément Dupont in his thesis defined something called a bi-arrangement, where you have hyperplanes of two types and you have a double complex. It's a generalization of Euler-Solomon. And it seems to me that that complex should calculate the dimensions of the ranks in Chen's unipotent completion. Is that related to what you're saying, or is that relevant in any way?
So yeah, so I think it's so. Thank you for the very interesting comment. Yes, so I kind of at some level I heard about this, but I have never really studied it. I think it is. So I think that this it's so I don't know this by arrangement. This we have not studied it from this context. This is something maybe we should look at. I think it is related to what I was saying here, that most of the research done in this area is in the world of quadratic algebras, and you basically make modules over the cohomological algebra, and there. And you can interpret. So the question is that. Yes. So what are these Causal modules there? You take the kernel of this K-product map, and you take the quotient of the exterior algebra by the ideal generated by this kernel, and you take the torus of that. Yeah. And you apply to this BGG. So actually, there's a lot of work on this category. Yeah, over exterior algebra. If you apply to this BGG, then you end up with our definition of Causal modules. But from the beginning, we sort of ignore that stuff, and we translate it into our terms, so to say, and we continued from there. And we did algebraic geometry with these Causal modules.
I see.
Now, I would say that in this, one would have to study what has been done and apply the same machinery to bring it in this world. But our work is entirely in terms over the symmetric algebra. And so this theorem, for instance, maybe I talked the previous one, is at the end of the day, this is some sort of kind of high power bot vanishing on some flag varieties. It's really algebraic geometry, the proofs of this.
I see.
So it would be, I think,
this
quite profitable to look at it. Yeah.
Sorry, I apologize.
Sorry.
You're very crackly. I was just making the simple point that in this Bailinson business, you don't need anything like you don't need any causality. It doesn't need any quadratic presentation at all. It works in general. So I don't know if that maybe gives a different perspective.
Yes and no. So this definition, of course, of the causal module, there is, of course, I don't need to put myself in wedge 2V. I can take a subspace in another exterior power, and I can take the same definition. Yeah, it's whether they can be studied. They have not been studied, these causal modules, but they can be studied. There is whether they are perhaps related to higher homotopy groups of spaces that I don't know. It's possible. And also this concept of resonance has been pursued by lots of people for differential graded D algebras and so on. But of course, you do not get immediately results so precise somehow that this is a formula exactly for.
So can I ask you? I didn't. Did you define the resonance for X in general on the previous slide? You defined a resonance for V on the page, but I didn't quite catch the resonance for general projection.
Yes. Here is the definition of the resonance. If you got it, I don't know. Here is the definition of the resonance. Essentially, you just intersect this projective space, the K perp with the Grassmann. So these are jumping. So essentially, they are jumping loci in cohomology.
For a smooth projective variety. My question is, how do you define the resonance? So in the next slide, I think.
I take the fundamental. Yeah. So right. So I define the resonance for I define the resonance for any subspace in wedge 2V. Now I take a space. I take the K product map.
Okay.
And then I take the resonance of that.
That's
the resonance for space. Yeah.
Thank you very much.
Sure.
Are there further questions or remarks, please?
One quick question.
Go ahead.
So these Causal module you defined, maybe this is incorrect, but it seems to be related to Tor2 or Tor2 over the dual coalgebra with your relations K. You can think them as quadratic relations, right?
Yeah, exactly.
That you're setting up Tor2, and in that case, what happens with higher 3, 4, and
right? Yes, that's what we are studying. Yes, but we are not saying it. Yeah.
And but is all information contained in level 2? Like once you know something about 2, 3, and 4 kind of don't matter anymore. Is this something that you observed or?
Sorry, can you repeat the question? So
could you say a short sentence as to why 2 is kind of the key cohomology degree that influences your?
Well, because we are looking at the first K product map. Yeah, that is the reason.
So
and, yeah, if you were to take some invariants out of the higher homotopy, of course, that's then of course other resonance would come into play.
So the massive product, for example, would have to do with Tor.
Exactly. Yeah.
Right. Okay.
Yeah. But that has not been done yet, so to say, in the sense that you can define, there is various possibilities for causal modules. Then the resonance would be just a support of the corresponding causal module. Now, whether you have such a nice description of the support, that's not clear, right? I mean, here you have you know, so the way this goes is that, yeah, relatively with easy techniques, you can show that the support of the causal module is the resonance, which has a very strong algebraic footing. And then this being given, you can ask more refined questions. Namely, what are the pieces, how big are they, and so on. If you take another picture, yeah, you would have to describe there is work on this, of course, by various people, but yeah, when it's not clear what, yeah, there are for free manifold, there are various pieces of works when the resonance has some sort of reasonable description, and the resonance in that case would be the support of the corresponding causal model. Because that's I define the resonance, but the point here, why the definition makes sense, is that exactly what I wrote here, that the resonance is the support of the module over the projective space. I should say there is a lot of interesting causal modules that have nothing to do with fundamental groups, and they have also led, so some of these causal modules have led to important progress on syzygies of algebraic varieties. So there is something to be gained by taking this larger view, leaving the groups behind and looking at the purely algebraic context.
Thanks. Are there any further remarks or questions? Well, if not, let's thank Gavril Farkas again. Clap, clap.
Yeah, thank you.
And we reconvene at 2 o'clock.